Hey everybody, so we're continuing with areas between functions day 2. So yesterday we did this problem. Find the area of the region in the first quadrant that's bound above by y equals the square root of x and below the x-axis and the line y equals x minus 2. So the first thing we're going to do is remind ourselves of what this picture looked like. So let's draw this graph. All right. 1, 2, 3, 4. Okay, so I am going to use red to do y equals the square root of x. So I know that it starts at 0, I know 1, 1, and I know 4, 2. And so this is the square root of x. And then we've got the line y equals x minus 2, so that starts at negative 2 and has a slope of 1, so up 1 over 1, up 1 over 1, up 1 over 1, and up 1 over 1. And we've got a straight line there. I should have brought my straight edge and I didn't, so I apologize. Hopefully you have yours. There we go. Okay, so what we have to pay attention to is we're also looking for the region that was bound at the x-axis, right? So here's the x-axis. So above by that, below by the x-axis, and then there's that line. So we're looking at this region right here. So what we noticed in class yesterday was that in order to do this, we have to use two separate integrals. And the reason for that is we're always looking for that top minus bottom. But what we notice is that if we look at the line x equals 2, so I'm just going to roughly draw that through for us, if we look to the left of that, then the top function is the red, the square root of x, and the bottom function would be 0. It would be the x-axis. But if we look to the right of the line x equals 2, then we know the top function is the red, the square root of x, and the bottom function is now this line, y minus 2. So we had to set up two separate integrals. So we had to do the integral, and let's see what our bounds were. We started at 0, this was our 2, and then here's 4. So we're going from 0 to 2 of the top function, which is the square root of x, minus the bottom function, which in this case was 0, dx, and then we have to add the second integral, which went from 2 to 4, and we know that the top function was that square root of x minus the bottom function, which was x minus 2. And then we have to close our integral and put dx. So when we did this yesterday, we had to do those two separate integrals, and so this was really a challenging problem without a calculator because of that. If we have to do these antiderivatives without calculators, there's a lot kind of going on there. And so really, the reason that this is a challenge is because the boundary functions change within the interval. So in other words, what the top and bottom functions are change throughout the whole interval. And so we need two integrals. Which can be kind of a pain. So today what we're going to talk about is we're going to learn a new way of solving these area problems that can make some of these problems easier. Not all, I'm not promising you a cure-all, but some of them will become easier. This method involves integrating with respect to y. So what I want to point out really quick is when we did this problem, everything was in terms of x. The bounds that we had, 0 to 2 and 2 to 4, those were the x values. When we look at the actual functions themselves, they have x variables in them. So if we look here, it's the square root of x that has an x variable. And same thing here, square root of x, x minus 2, they have x variables. Which means on both of these, or well, for both of these, the functions had y isolated. Y was by itself, so it said y equals blah 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 something with x, right? So we have x values for our bounds, our functions have x variables, and then we also have to notice that this was dx. We were taking the antiderivative with respect to x. So now everything that we do for these problems, well, not all of them, but we're going to do with respect to y instead. So we're going to have an integral, and we're going to have the lower y value and then the upper y value. So these are no longer x, these are y. And we're going to take the integral of, now it used to be that we would do top minus bottom. So instead, we have to do right minus left. And then when we close our integral, now it's not a dx anymore, now it's dy. So instead of top minus bottom, now we're doing right minus left. So I want to show you guys something really quick. You don't have to do this with your packets, but I'm going to turn my graph here really quickly. And I changed it so that the positive x-axis is now going up. So if we ignore that line I drew in at x equals 2, if we look at this region that we want to find the area of, we can see that the blue function is on top the whole time, and the red function is on the bottom the whole time. So if we go back to our normal graph, that's the right minus the left. Okay? So let's actually go ahead and do this. So this is the same problem as above. So I'm going to go ahead and draw our picture, just a rough sketch now because I know what the intersection points are and I kind of know what's going on already. So I know I have my square root function here. And I have my line here. Again, very rough sketch. But what I want to point out now is now I'm taking the integral with respect to y. And so I'm actually going to draw my lines going this way now to symbolize the area that I'm trying to find. All right, and now we need to do our integral. So what we have to remember is that both of these right now are written in terms of y. The y is isolated. So if I look at this function here, y equals the square root of x, if I want to solve for x, that's just going to be x equals y squared. And for this one, I need to isolate the x now, so it's going to be x equals y plus 2. So now I still have the same functions, it's just now the x is isolated on both of them instead of the y. And I'm going to go ahead really quick, I'm going to look at these bounds that we have here. So we know we started at 0, that's our lower y bound. And we need to know what this point is right here. We know that intersection point is the point 4, 2. And again on our integral, we want the upper y value, which means this is going to be 2. So we want the integral from 0 to 2. and we need the right function minus the left function. Now if we look here, my colors are actually flip-flopped then, because my right function is actually the blue one, which means y plus 2. And then minus my left function, which in this case is that square root of x, but again I want it in terms of y, so that's my y squared. And then I'm going to close my integral with a dy. And now we're actually just going to grab our calculators and have it calculate it for us. We're not going to do this one by hand because we've got a lot of other stuff to look at. So we're still going to do Math 9, and we're going to integrate from 0 to 2. Now your calculator is always only going to integrate with respect to y, so we're going to change all these variables to y when we put them in the or x, excuse me. Sorry, I misspoke. X with our calculator. So we're going to do x plus 2 minus x squared, and then we're going to do dx, and we get 3.333. Which is the exact same answer that we got yesterday in class when we did the example up here with the two separate integrals. Okay, let's do another example. So here's question 2. So we have to make the choice. Find the area with the region enclosed by the graph y equals x cubed and x equals y squared minus 2. So we're going to do it twice. We're going to do it with respect to x, and we're going to do it with respect to y. So before we do anything, we need to make a graph of what's going on here. So let's go ahead and do that. Again, you should probably have your straight edge out and make sure that you're drawing it a little bit straighter than mine and a little bit nicer than mine. But let's see here. If I want to graph y equals x cubed, that's 0, 0, 1, 1, and 2, 8. And then I have negative 1, negative 1, and negative 2, negative 8. So there we go, there's that. And then my other one is this x equals y squared minus 2. So because that's got the x isolated, I'm actually going to make a table here and kind of figure out some values to put in. So since it's got the x isolated, I'm going to plug in y values. So I'm going to plug in negative 2, negative 1, 0, 1, and 2 for my y. So let's see, negative 2 squared would give me 4 minus 2 is 2. Negative 1 squared is 1 minus 2 is negative 1. 0, it would be negative 2. 1 would be negative 1. And then 2 would be 2. And so I can go ahead and plot those points then. So 2, negative 2 would be right here. Negative 1 would be right there, so they share that point. Negative 2, 0 would be right here. Negative 1, 1 would be right here. And then 2, 2 would be right here. And so this is a parabola this way. There we go. Sorry, I don't know why that's so squiggly. My bad. Okay, so there we go. If we are going to do this with respect to x, then the area that we're looking for is right here. But that means we need to figure out this intersection point. So we know this one right here is negative 1, 1. But we want to figure out what this point is right here. So let's go ahead and grab our calculators. And we're going to have to go ahead and plug these in. So let's see, x cubed, that's easy enough, so x to the third. Now, if I want to do x equals y squared minus 2, I need to isolate the y first. So if I add 2, I'm going to get y squared equals x plus 2. And then I'm going to need to take the square root. And so I need the plus or minus the square root of x plus 2, because that's actually the blue curves that I graphed there. So I'm going to do the square root of x plus 2, and I'm going to do the negative square root of x plus 2. And we're going to go ahead and do our standard zoom there, and hopefully make sure that my graph is correct. Okay, we are good to go. So let's go ahead and take a look there and see what that intersection point is. So intersect right there. So 1.215. And then I'm actually going to go ahead and put the y value in there too, 1.793, because we're going to need it on the next part. So that's the x value that we care about right there though. So when we look at this graph here, we can see that, I'm going to zoom in a little bit, the top function is the blue, this blue, the whole time, but the bottom function changes from blue to red. And so we have to be very careful while we're setting up our interval here. Okay, sorry, I totally just got distracted. My bad. I was checking to make sure I had the right values. That was my bad, guys. So let's look here at x equals -1, because that's where it changes. At -1, or from -2 to -1, it's blue minus blue. And then from -1 to 1.215, it's blue minus red. So we're going to go ahead and set up those integrals. So the area, so we're going to do from -2 to -1, because those are our bounds here. And we have the positive blue minus the negative blue. And so we're going to do the positive square root of x plus 2 minus the negative square root of x plus 2 dx. And then we're going to have to add the next integral, which is going to be from -1 to 1.215. And now if we look at the top is still that blue, but it's the positive square root portion. So the square root of x plus 2. But now we're going to do minus the red function, which in this case is going to be x cubed. And then we'll close off our interval with a dx. So again, we had to do the two separate integrals because the functions ended up changing. From -2 to -1, it's blue minus blue. From -1 to 1.215, it's blue minus red. And so that's what we're doing in here. So we're going to go to our calculators real fast, and we're going to figure that out. So Math 9, -2 to -1, the square root of x plus 2 minus the negative square root of x plus 2 dx, and then plus Math 9 again, from -1 to 1.215, square root of x plus 2 minus x cubed dx. And hopefully I plugged that in correctly. 4.215 would be our answer here. And so there we go. There's our answer with respect to x, when we integrate with respect to x. But again, that was kind of a lot of work, right? So instead, we're going to look at what happens, how much easier it is when we do with respect to y. So what I'm going to do real fast is I'm going to get my other function here to have the x that's isolated, which just means we're going to have x equals the cubed root of y. And then here, this x is already isolated, which means that's already easier for us. So let's go ahead and just redraw our sketch real quick. So we know we've got our parabola that kind of looks like this. I don't know why my hand is shaking so bad. Sorry, guys. And then we have our cubic function, which is kind of like this. And now we're going to integrate with respect to y, which means we're going to go this way. So if we're looking at doing right minus left, the whole time this red function here, this cubed root of y, is going to be the right function, and then the left function is going to be this x equals y squared minus 2. So we don't have to worry about having two separate blue functions for this integral, which is really kind of nice. So the area is going to equal, we want the lower y bound to the higher y bound. Well, we know that here is -1, because that was the point -1, -1. And then this one we want the y value for is 1.793. And again, we're going to do right minus left. So that's going to be the cubed root of y minus the left function, which is this y squared minus 2. And then we're going to close our integral and put a dy. Ooh, okay, that is dx. Never mind, we're good. I almost just messed myself up again, guys. Okay, so let's go ahead and put that in our calculator and make sure we get the same answer. Again, for our calculator, we're not going to put y, we're just going to change those y's to x's. So math 9, -1 to 1.793. We want the cubed root of y, which means hit math and go to number 4. We're going to do x minus x squared minus 2. And we're going to integrate with respect to x. And we should get the same answer if I plugged it in correctly. There we go, 4.215. So we have to sometimes make decisions on which one's easier. It's not impossible to do this integral with respect to x. It's just easier to do it with respect to y. So we'll talk more about it in class. I know I kind of rambled a little bit in this video. I apologize. I'm a little out of practice. We will do question 3 together in class to make sure you guys are good. So I will see you later. Bye.